This is the Debunking Economics podcast with Steve Keen and Phil Dobbie.
The archives.
Episode 153. Steve Bannister pours cold fusion on climate deniers.
Well, it's not just me and Steve Keen this week. Steve Bannister is joining us to talk about his model for climate change. Now, we know Steve Keen isn't a fan of the Nordhaus model of climate change, this year's Nobel Prize-winning economist, who seems to indicate that climate change won't be too bad on the economy. Well, Steve Bannister's model paints a very different picture, a more alarming picture, and he pinpoints the one variable that needs to change is the one that's hard to change. So, we need to look at alternatives when it comes to energy. That's this week on the Debunking Economics podcast. So, Steve, tell us about yourself, first of all, briefly. Tell us about your work, what you're doing at the University of Utah, and how you came to be involved and interested in climate change. Where did it all begin?
Yes. So I was in private sector, high technology for much of my career until about a decade ago. And that's actually what first led me to Utah. I was at a software company named Novell.
Which we both know pretty well, don't we, mate?
Yeah, absolutely.
So I was a director at Novell at their headquarters in Utah, and that I got out to Utah in the mid-1990s. And then as I got more gray hair and started thinking about retirement, I said, I don't want to retire, but I did want to get out of high tech. And I had done an undergrad in econ decades ago and still loved it. And I said, gee, I wonder if I can still hang with the smart kids. And I wandered onto the campus of the University of Utah, a very beautiful campus right up against the mountains, beautiful. And started talking to a couple of the economists, and they were looking at me like, you're crazy, old man. But they accepted me in the program to finish my PhD. I did that. They offered me an appointment, so I'm now in the faculty there and teaching and doing research. And that led me, my dissertation was essentially on the English Industrial Revolution, which I describe as primarily an energy revolution. Yeah. And that led me into the kind of modeling I'm doing and therefore into climate change.
So I could see right there why you're getting on so well with Steve Keen about the importance that energy plays in the Industrial Revolution and beyond. But you also, I guess the other thing you both got in common is, looking at climate change models. They're pretty much rooted in conventional economic thinking, aren't they? If we, for example, I know Steve Keen, your criticism of the Nordhaus model, and a lot of these models, because they're developed by economists, they're still looking for an equilibrium. We've got to, if we can find the right dynamics, we can counter them with policy, and then we can all live happily ever after. That's pretty much the thinking, isn't it?
That's correct, and it's even further than equilibrium. For example, the Nordhaus model and many macro models that are in the mainstream today are what we call micro foundation based. They're based on utility maximization by individuals, spread out over time and discounted back and all that kind of stuff. And all that is pretty much total nonsense from a reality standpoint. And the more years you're trying to project or forecast into the future, like the climate models do, the more nonsensical it becomes.
So Steve Keen, your issue with the Nordhaus model, of course, Nordhaus is this year's. What's going on there? I'm going to have to edit this now, aren't I? So Steve Keen, your criticism of the Nordhaus model. We should mention that Nordhaus, of course, is this year's Nobel Prize winner. He's developed his dynamic integrated model of climate and the economy, the DICE model, which is basically a bit dicey. Just in a nutshell, your concerns about it. It's the input, like all of these things, it's the inputs, isn't it?
Yeah, well, it's the old story, garbage in, garbage out. What you can actually say with Nordhaus, it's garbage in, fan in the middle, garbage spread everywhere on the way out because the shit hits the fan, and the fan is this neoclassical growth model, which, again, Nordhaus is based on the vision of a guy called Frank Ramsey, who was a 1928 mathematical prodigy who built this little model about what's the optimum savings rate for an economy. And he imagined the existence of an all-knowing social planner who knew everybody's tastes, knew the technology was going to evolve over time, and then could work out what he literally call it the bliss point in the far future, where you get the trade-off between utility maximizing behavior by consumers and profit maximizing behavior by firms reached an optimum. And that happened to be unstable, so the only way to get there was to move where you were currently to get on the unstable path along a saddle. It's like you want to jump onto a horse. You're a ball bearing and you want to jump onto a horse. So it's vitally important to jump onto the horse from right behind its ass, because if you don't do that, you'll bounce off the saddle. So the social planner worked out where to jump to, and then you oscillate up and down the saddle, and that's what gives you the trade cycle. That's sheer bloody nonsense, which was the foundation, but that's the fan. The shit that's fed into the fan is Nordhaus's assumptions about climate change, and these are literally just assumptions. One is that you can simulate the impact of climate change with a simple quadratic. So a 1 degree increase in temperature causes X percent damage to the economy. A 2 degree causes 4X. A 3 degree causes 9X. Yeah. A 10 degree causes 100X. And X is an incredibly small number. And why is it a small number? Because he based it on what happens to GDP when you move, when you compare Washington to Dallas. And so if Dallas is 10 degrees warmer than Washington, the GDP is a bit smaller. But he extrapolates that into oh my God. So
that is how you get a 6 degree temperature rise is going to reduce GDP by 8%, which is slightly at odds with the IPCC, which says that actually 95% of the world's species are going to be wiped out. There's going to be vast amounts of methane, which are going to be released from the seabed, the consequences of which could destroy terrestrial life almost entirely. That sounds like it would take more than an 8% hit on GDP to me.
Yeah, I know. And you read this stuff and you basically think, look, I'm in Amsterdam, but they don't sell anything that good here. It is so damn delusional. It's such fantasy stuff.
Right.
And so what Steve and I are both doing is fighting a rearguard action with realism against this nonsense. And it involves two things. Of course, I'm trying to demolish Nordhaus, and I'm building, working with Matthias Rosselli and Tim Garrett, who's actually a colleague of Steve's at the University of Utah. We may indeed be saved by the Mormons. Believe it or not, we are building alternative models, and Steve has one of his own as well.
Well, yeah, I imagine the Mormons are not big energy users. I might be wrong on that. Perhaps that is the answer. We all need to change our outlook on life. But Steve, I'm glad you both spoke at the same time, by the way, because I wondered whether you actually were the same person, and I was just talking to two voices inside Steve's head. So, Steve number two, tell us about a better model then than the Nordhaus model. What are because it is obviously it is a question of what you input into the models, but also what it does in the middle, and you don't want that fan where everything flies everywhere. So what's the ideal model when we're looking at modeling climate?
The way I got to my model, let me explain that. I did look at the Nordhaus stuff fairly early in my dissertation work. So that would have been a decade ago. He had a model I think he called RICE before the DICE
regional
model.
No, regional came after DICE. The DICE came first.
Then RICE.
RICE is regionalized DICE.
But anyhow, I started looking at that stuff, pulled down the spreadsheets, started looking through the calcs, and I immediately went, called bullshit on it and abandoned it, as opposed to what Steve Keen did, which was totally deconstruct it and try to tear it down, which is extremely useful. And so I was looking for a different approach to modeling, to do IPCC style modeling, that is the economic front end to a climate model, that would be a much more realistic alternative to Nordhaus. And I happened to read, as part of my research, an article that was in the Proceedings of the National Academy of Science, 2009, if I'm right. I think that's right. Written by a group of researchers led by a Japanese fellow named Kaya. And
Kaya.
Yeah. And they did a descriptive regional model, describing using a certain decomposition of actual data, not theory, actual data on GDP, on carbon emissions, on energy consumption, and on population. And you take those parameters and you create ratios out of them that I describe in my model and in the paper you have. But essentially, it's a very simple model. It takes GDP per capita, which is living standards, and the Kaya people called it GDP intensity because they're scientists. And then you take the energy intensity of GDP as a ratio based on the actuals. And then you take the carbon intensity of the energy supplies, all energy sources, all primary energy sources, so both carbon-based and non-carbon-based, and as a ratio of the total energy. And you end up with those three ratios, which are descriptive. And I have come to believe they're structural. That is, they're pretty fundamental in the system.
And how do they change? Because imagine if GDP picked up, or the intensity picked up, as they said, then obviously we're going to start using more energy.
Correct.
And we'd use more carbon, but we'd also maybe get to a point where we actually start to go beyond that. And we, for example, might start to use less coal. So carbon intensity is not going to increase at the same rate as energy use, for example.
Right. Yeah. My starting point were those three ratios, and then taking the actual data and calculating those at a global level since the data was consistent enough, which is about 1980 through to recent times, to do that globally, look at those results, and then decide what to do. And the results scared the crap out of me because, especially on the carbon intensity, after about 2000, we were doing actually pretty well in reducing carbon intensity. The curve was headed in the right direction. But after 2000, it reversed itself by about a third, and we were going in the wrong direction. And it's easy to blame the Chinese, and that's partially true, but it's not the entire story. But at any rate, the whole world was going in the wrong direction, and that was very scary to me.
But that was driven by the growth in GDP, presumably.
Well, yes. All these things end up interacting. It's a multiplicative model, right?
It's a very simple model, actually. Imagine all you do is have a ratio, and this is often done. Even Bernanke's done this at one stage, trying to find the cause of the Great Depression. Right. Just use the wrong bloody ratios. So it is important to choose ratios that are correct. I mean, to give you Bernanke's case, he had a ratio between the amount of gold, the Federal Reserve, and the money stock, as if gold determined the money stock. Well, I'm sorry, he's wrong, and therefore those ratio analysis was incorrect. Yeah. But this what's called Kaya identity simply has the amount of CO2. I think it's what CO2 produced by the industrial system.
They call it flux, which is
the flux of CO2. The CO2 output per year is, you can break it down to CO2 divided by energy times energy divided by GDP times GDP divided by population times population. And then what you're doing is saying each of those is a causal factor. Right. And then what you simply do, this is a typical little mathematical exercise. The rate of change of the logs of all of those converts that from a definition to a statement of rates of change, which is what you're actually then analysing.
And out of that, what you get then? You get what the impact is going to be on the climate out of this. Yeah. So what is the temperature change?
So and by the way, let me just one brief aside to support this methodology. The IPCC actually uses this methodology to assess the various climate models that they look at. They've used this as a measurement and a way to compare across climate models. They did this in their 2000 SRES study, special report on environmental something, whatever, SRES. And what I did was I took the model, the decompositions, the ratios, and said, since I can claim, and it's mostly correct, statistical independence between them or among them, I'll forecast those individually, okay? The ratios, so GDP intensity, carbon intensity, and energy intensity.
And population, yeah.
And then take a population forecast. I don't, so far, I have not separately done my own population forecast. I take typically from the UN, they update that frequently, but I take that and then you multiply through the UN population forecast and my forecast of each of those ratios. And as intermediate outputs, what do you get? You get levels. You get the level, first of all, of GDP, total GDP, going out as far as you want to forecast. You get the total level of energy consumption. Again, over the same time period, you get the total level of carbon dioxide flux over the same period. So that gives you, and it's all based on real data that's been forecast using the best method I'm aware of. So it's as realistic as I know how to get on given data, on actual data.
And what do you find from that? Because population is going to slow. Obviously, the more countries become developed, we're going to see that's going to slow. GDP growth obviously is going to increase as they become more, as economies pick up. But as we were saying earlier, maybe at some point that carbon intensity will start to slide as well, and the population is not growing as much. That sounds like a good picture. It might take too long, but it sounds like things are starting. I don't want to use the word equilibrium, but it sounds like things are starting to level off a little bit, aren't they?
Well, that's correct. So when you do all of that, given conditional on what population forecast you start with, but the one I'm using right now, it looks like total global GDP output will level off and then start declining somewhere around 2085 or 2090.
Right.
And before that, both energy consumption and carbon dioxide output peak and start declining. Yet, while all of that is happening because of the dynamics in the system, the living standards are likely to continue increasing. So given the data, given the forecasting methodology, living standards globally will continue to increase, and eventually we will reach a peak of output, GDP output, and therefore resource consumption, and then start heading down.
But that's at the same time that I don't know you have done this yet. Have you looked at the temperature implications?
Yes.
And what are they?
Yeah. So in the long run, there's good news. It's sort of an inverse Keynesian situation. Phil.
You're not going to tell me the bad news is, but we're all going to be dead by then, so it's too late.
Oh, you spoiled my punch.
You got it exactly. In the long run, we're fine. In the short run, we're going to fry.
Right. So what in your model? Where does the temperature peak then?
Yeah, high 3s, low 4s centigrade.
Right.
And then when you then look at what the climate scientists are saying about that, and on this front, I'm in touch with the people who are writing these papers now, because I don't think they were aware of just how badly Nordhaus distorted their work. But they are saying that a 2-degree temperature, it will be sufficient to trigger several what they call tipping elements of the Earth's climate, causing a cascade that will drive us well beyond the 2-degree level. So once we crack 2 degrees or get close to 2 degrees, and we're not particularly far from it, even on Nordhaus's calculations of temperature change, we're 25 years away from 2-degree increase. It's that tight. I said, we get to that level, all these systems cascade on one another. We'll go through maybe 5-10 degree increase, and at that point, it's extinction time.
But Steve, it sounds like from your model, what you're saying is that it is the growth in population and therefore the subsequent growth of GDP as economies become more developed, which is why a lot of people in the West say, yeah, well, what can we do? It's all China's fault, as you said yourself.
Yeah, Noel, I try not to totally blame China. I would, if I were
you want to blame India too, and
I blame America for getting there first.
If I were the emperor of China, or the dictator, or whatever he is, I would do exactly the same thing. I mean, I don't blame him for doing what he's done. Right now, so the real issue in this, when we're looking at carbon dioxide, is our energy sources. And that's what's got to change, because I don't think much of the rest of the system is going to change until we get to one of these tipping points, which, by the way, I don't incorporate tipping points in my model because I'm using actual data. So when tipping points occur in the real data, then they'll be in the model. That's how my methodology works, right?
Right. But I mean, if those tipping points haven't happened yet, how do you know that? Because I mean, that's one of your criticisms, isn't it, Steve, of the Nordhaus model? It totally ignores tipping points. And
this is where people like Lenton, who's the person that Nordhaus misquotes. And I've revised the document I'm writing, the paper I've sent to patrons already, from saying that he misrepresented to say it's a lie. I just want to quote these out on screen, on the podcast, to get an idea of just how blatantly he has effectively lied about what they said. This is Nordhaus. The current version, meaning his damage function, assumes that damages are a quadratic function of temperature change and does not include sharp tipping points, but this is consistent with the survey by Lenton. Then you read Lenton's conclusion. Society may be lulled into a false sense of security by smooth projections of global climate change, which of course you get from a quadratic. Our synthesis of present knowledge suggests that a variety of tipping elements could reach their critical points within this century.
And these tipping points are not economic tipping points, are they? They are. They're climate tipping points. So,
right.
So surely they have. Yeah, they surely have to be in them, because there's going to be a point, for example, where plant life starts to absorb a lower proportion of carbon dioxide. That's not a linear point. There's going to be points at which ice has melted and it can't melt anymore. You know, so that's a physical constraint.
Or methane releases, or whatever, right?
So you haven't got those in your model, and
no, because of my approach. I mean, I'm using real data, right? That's what's different about my model from all these others. And I always get asked or even attacked saying, well, what about this scenario, that scenario, tipping point scenarios, and so forth? And I go, look, I could, every person I talk to will give me a different scenario. How do you want me to model that, sir or ma'am?
In fact, what you could do on that front, just to actually answer that question, and we're going to have a crack after we finish this conversation of putting this Kaya model into Minsky and linking it to data as well, is that if you look at the Stefan article, Stefan 2018, which is a follow-up to the Lenton article that Nordhaus lied about. In the Lenton argument 2008, they were trying to identify sort of continental scale elements of the planet's biosphere that could be tipped. And they, of course, obvious ones, the Greenland ice sheet, Arctic ice, West Antarctic ice shelf, coral reefs, yada, yada, yada. And now, having identified them back in 2008 and 2018, they've said, okay, these are the tipping points. These are the influences between one tipping element and another. And these are the temperatures at which they think they're triggered. So the Greenland ice sheet, they've got being triggered between 1 and 3 degrees Celsius. Arctic summer ice, the same. West Antarctic ice sheet, the same. And then each of these will affect others. The coral reefs, they've also got 1 to 3, but the coral reefs don't affect anything else. So they're looking at the interactions as well. So they've come down and quantified it and said 2 degrees is that if 1 to 3 is likely to cause major things like Greenland ice shelf melting, West Antarctic melting, we're talking 70 metres of ocean ultimately out of those changes, then we shouldn't get past 2. Now, what Steve could do with his model, which would be an intriguing thing to add, is that with your Kaya equation, you get a prediction for temperature. Okay. With the prediction for temperature, you could feed that back into the Kaya model.
And come up with some kind of a tipping
and say, okay, if you say that if the 2 degrees is the point at which it all breaks down, then you have one trajectory without tipping points and another with.
And again, I totally agree. And that would be a nice extension. However, I've avoided doing that, partly because there's so much controversy around these tipping points. I mean, we have one article here, but someone else will say, oh, that's just wrong. You got to do it this way. And I've just avoided that and say, look, here's what my model says. In a sense, my model shows the best case.
Yeah, it's going to say it's going to be more. If you throw in tipping points, it's more alarming. But what might make it less alarming? What about things that are happening now, which might be influencing data? Like, for example, and this is obviously the argument used by climate change skeptics. We've got sunspot activity. We've got solar wind activity. How much is that influencing the historic data that you're putting into your model?
Well, it's all, I mean, everything is in there. So the answer is it's all there, and it's all there in whatever the statistical mix in history is. So I don't focus on that very much at all. And if you're asking me to look at that going into the future, again, it's in the scenario space that I try to avoid, because it just gets far too complex for people to digest. I mean, I get arguments in audiences among the audience when they're talking about scenarios. They're arguing among themselves. So I just go, look, this is best case. And by the way, the best case is so scary in the short to medium run that we better start focusing in a different direction than most people are looking.
So how far does your data go back? What's your history on this?
Yeah, so the global database that I use comes from, well, GDP data is widely available globally. but the carbon dioxide emissions and the energy input emissions by country and therefore globally are compiled mainly by the EIA in the U.S., part of the Department of Energy, and that goes back to 1980. The complete database goes to 1980.
Right, which people would say is actually quite, it's a short run.
Yeah,
it's all available, but it's not a long time.
Yep. If I had more data, I'd go back further.
The funny thing is, even if you do that, you're still talking about, I think, a temperature range from 0.3 above pre-industrial levels to 0.9 above pre-industrial levels. So even over that 30 of 35 years, it's been a substantial increase in the globe's temperature.
So the conclusion is population is the key factor then. That's what we're basically saying.
In the long run, absolutely.
But we need to do something in the short term, but less population growth. Thank goodness we invented computer games, because that's going to, from what I can tell, is going to stop us procreating. We just need to, maybe God has given us computer games to try and save the climate. Perhaps that's, if there is a God, maybe that's what he's doing. What do you do with this when you have models like this? Because there's so many models around, all giving conflicting scenarios. And it sounds like, where does yours fit in the middle of all of that? Are you sort of like the middle ground, or are you one of the...
Well, so I occasionally look at my outputs when something new comes out, one of the IPCC models. They do all of these ranges. When they look at combinations of their models, do ranges and estimate essentially the same parameters I'm forecasting. And I do comparisons, and I come out, I think, sort of really pretty close to where they come out. But I do it in such a much more simple and understandable way that it's night and day to me. So, and I have a high degree of confidence in the data, and I'm using, again, the best forecasting I can, which is pretty darn good, actually. It's a fairly modern, up-to-date time series forecasting methodology. And so I think I have a high degree of confidence in my results, conditional on not having tipping points, right? If tipping points occur, it's going to get worse. So I just stop there, Phil. I just say, this is bad enough, folks. we had better change. And when I get in front of economists who are degrowth or zero growth economists, and they're howling at me over what I'm saying, frankly, because I say we're not going to stop per capita growth. You're just not going to do it. Tell me how you're going to do that. You got to go kill the people or have major recessions to stop that growth.
Well,
right?
So does that mean, so what you're saying is when we drive electric vehicles and we say we're not going to burn coal anymore, we're going to use less energy generally, or we're going to eat less meat so there's fewer methane producing cows. You're saying that doesn't make any difference?
No, it does make a difference. Everything does make a difference, but all of the differences that we've accomplished so far to date that are in the data don't affect the long run sufficiently at all. We're still screwed in the short to medium run, so we won't get to nirvana because we'll fry, and that's what's led me to I've sort of been forced into looking at true alternative energy sources that are different than what we have in the current renewable fleet, the wind and solar energy and some of the other technologies that are in the current renewable fleet, because all of those are in my data and they're not making enough of a difference. And as an economist, I know why. There's not enough price differential.
Right.
Well, it's partly it. I mean, the other thing is that we've got a very low energy return on energy invested.
That's correct.
That's probably the major issue.
And by the way, the current fleet of renewables is extremely low energy density. It takes a great deal, which is part of the return.
Yeah.
It takes a great deal of physical space in order to generate sufficient output, and that's not going to be sustainable in the long run, right?
But they would become more viable, and we can look at what those sources of energy might be, but presumably they would become more viable if your model or models like it were actually used by economists developing their pattern for the future. The problem that you've got a president in the United States who thinks it's all a hoax brought about by China to try and slow down the West, and the Australian Prime Minister's not far behind. We've got all these climate change deniers making decisions. But if it was accepted, and we had central banks, for example, looking at all of this data as an input to managing the economy, and treasurers doing the same thing, we would take a very different approach to all of this. And all of those other sources of energy, if there's no choice, would all of a sudden become affordable.
Or become considerable.
Well, they could, they could be subsidized sufficiently. That's correct.
Yeah.
However, see, my approach is actually, I've evolved my approach, and it's quite different today. What I've done, more or less in parallel with developing this model over the last 7 or 8 years, is look at the physics, the new physics, potential physics in energy sources. And there's some very interesting things going on there.
No, I might just dive in here quickly, by the way, because I'm interested in some of this stuff as well. But this is one of the areas where we're getting into quite non-mainstream physics. I'm very happy with non-mainstream economics. You're all aware of that.
Listen, you've got
non-mainstream physics. So let's.
Steve Keen, you've had us all taking minerals off the moon. So
yeah, I know. Okay, fair enough. Asteroids, get it right.
Asteroids. I do beg your pardon.
And some centuries away, and using rockets. But let's go to.
But it sounds like this is our only choice. So I'm interested in all of this. Where do we get our energy from?
Just a little caveat there. Let's start with the conventional to the less conventional. Let's rule some of the things out.
Okay.
So we've said one of the issues with
wait a minute, Phil. You can tell I've got Steve Keen a little nervous here.
I know. I'm loving it. I'm loving it. I'm thinking, just how off the wall are these ideas going to be if Steve Keen is putting a caveat associated with them?
Okay,
so
let's start with the basic. The thing about solar and wind is that the very low density of the energy and the need to actually, if you ever gone past some of the new wind turbines, they're 80 meters tall of concrete. So to actually make them takes carbon to begin with on a grand scale. And then when you look at the energy return and energy invested, it started very low, something the order of 5 times as much energy back for the energy of constructing them. They're slowly climbing, but they're coming from a very low cliff. So that's one problem. At the other extreme, you can say, well, what are high-density energy sources that we haven't yet exploited? And here, Steve and I are in complete agreement, I think, on the potential for thorium reactors. And potentially also maybe some uranium reactors. I know a lot of my patrons, engineers working in the nuclear power space, they're saying uranium is reasonably okay. Some of them are saying thorium is much better. But if you do thorium, then that implies a high density, very high return on energy invested way of replacing the carbon-based stuff that we use right now. So that's inside the conventional science world, but as yet not properly engineered. So then,
and the issue, and I know experts in the field, in the fission field, from government and academia, and they're almost totally against developing future fission sources, whether it's thorium or whatever. And their argument is, look, the costs are just not there. Your cost is too high.
And disposal, obviously, is the big public concern.
Right, and the non-proliferation issues that arise from the waste.
We'd like to have a debate on Discord over this, because there are some people who are strong fans of thorium in the Patreon community.
Yes,
and they say that thorium is actually extremely low. I've seen this. There's actually saw a recent YouTube video of a company, I think actually based in the Netherlands, that was attempting to build thorium nuclear reactors which could fit literally in a 40-foot long container and would generate 50 megawatts of power. And they talk about community nuclear power systems, which they also say that the waste elements coming out of a thorium reactor have a half-life of 300 years versus the tens of thousands of years of half-life coming out of uranium-based reactors. And also they say they can actually use these reactors to degrade the plutonium waste into something which also has half-lives of 300 years. So there are arguments that are the other extreme, saying thorium could be.
Come on, get onto the more crazy ideas. I want to hear them.
There you go. Okay, no, I'm sitting back. Okay. I'll make some comments, but it's all Steve here.
Okay, so my belief is that that even thorium is as much of an improvement as it probably is over current fission technologies, is still going to be too high priced to really cause a displacement of carbon. Carbon's, as long as the price differential isn't sufficient, India is still going to go with coal, or somebody.
That's a good argument.
And so my view has been, let's find a really cheap clean source, like an order of magnitude or even 2 or more orders of magnitude cheaper than anything that's available out there now. And if you're going to do that, you have to go off into physics, and you have to go off into non-mainstream physics, frankly, because mainstream physics does not support some of the experimental work that's been done for quite a while, at least the last 3 or 4 decades. And there you get some very interesting possibilities. And I think both Steve Keen and I should back up a hair here and talk about the current fusion work that's going on, the hot fusion work that's been going on for 40 years at the bill of, I don't know how many billions of dollars around the world with ITER and tokamak and all of those that don't appear to be any closer to real results. So that appears to be a bit of a fantasy, frankly, a scientific fantasy. Yeah. So if that's not going to work, where do you go? And I have spent quite a bit of time looking at the physics and working with experimenters in the field.
Can I just say, this is the biggest build-up ever. It's, I'm sitting on the edge of my chair here.
I mean, it's needed because some of this stuff is going to sound, it's quite,
Come on. I'm on the edge. I'm so far on the edge of my seat, I'm about to fall off.
Okay. Well, we're trying your patience here. So I'm going to start with actually the institution that I'm at right now, which is the University of Utah. And 31 years ago, I guess now, or 30 years ago now, at the University of Utah, there were 2 scientists, Stan Pons and Martin Fleischmann, who made an announcement to the world, and pretty much the whole world was there, in the Henry Eyring Chemistry Building on the campus of the University of Utah. About what? About cold fusion. So they were pretty quickly excommunicated from mainstream science, exiled to France, and actually put up in quite nice style in France by the Toyota family of Toyota Motors, who built a lab so they could continue their research. So there were people that did believe, and there have been scientists around the world that have been doing, experimenting in that space, in the cold fusion space. The attraction of cold fusion is very high energy density at essentially room top temperature and pressure conditions. So it has all the attraction of fission without any of the waste byproducts or things like that, or any bad radiation output and so forth. So it was very, very potentially attractive. It's just very difficult to initially reproduce those experiments, and that's partly what got Fleischmann and Pons. But other scientists have kept up the work since then and are having, I think, actually increasingly good results, to the point where I know of 3 U.S. companies that are in the process of commercializing, and I'm probably missing some. I think there are probably more by now, this technology going to market. They're in the development phase to get this technology to market. One company actually has, 21 kilowatt heat reactor on customer sites, on paying customer sites. So it appears to be a real step in the right direction. High density.
So how does it work? So it's like nuclear fusion, but obviously much lower temperatures.
Yes. So the challenge in any fusion, you're trying to fuse 2 hydrogen atoms, right, to release energy, create helium, and so forth. Is getting over the so-called Coulomb barrier, which is the repulsive barrier based on the charges at the atomic level. And that's what hot fusion attempts to do. It attempts to create conditions where that is overcome and these atoms are smashed together. They overcome the Coulomb barrier and create the reaction you desire. And cold fusion appears to do that. All the scientific experimental evidence is it does the same thing, except with no high pressure and no high temperature. In fact, it creates a lot of heat, right? But it doesn't need heat in order to accomplish the reaction. And there are various mechanisms. There's still not settled theory. That's another part of the problem on how exactly this all works. It's new science, new physics. I have my own preferred explanation, theoretical explanation based on the physicists that I work with. But it's just as controversial as the next guys. I don't know if you want to hear all of that. But
we better hear it, I think. Yeah, let's have a listen. Yep.
All right. Okay, so the new modern physics, the 21st century physics, which is an extension of the older physics, the mainstream physics of the 20th century, incorporates some new mathematics. It's not actually new mathematics; it's old mathematics going back to 1920, but it's the same mathematics that theoretical physics uses, everywhere. Mainstream does, called differential geometry. The differential geometry was actually started, I guess, in the 19th century, probably mid-19th century, and used, for example, by Einstein when he did his relativity work. And it was sufficient, that geometry was sufficient to describe the curvature of space-time that Einstein incorporates in his theory, right? And but in the 1920s, probably maybe the best mathematician of the 20th century, French mathematician Élie Cartan, mathematically completed differential geometry. And it is the standard geometry that everyone engineering science uses today. Now, the difference between the Cartan and the prior was Cartan incorporated what's called a torsion component or term. So Einstein had the curvature, Cartan added torsion or spinning, okay? And that completes differential geometry. So you can develop explanations of complete explanations of physical systems that are very complex in four-dimensional space-time, for example, using this geometry. Now, the incredible irony is that most physicists do not use the torsion term. They acknowledge it, and then they throw it away. Modern 21st century physics, in my opinion, is going to incorporate that. And I know the people that are doing the theoretical work. In fact, that's why I'm going to Wales at the end of this trip I'm on right now. But once you do that, once you incorporate that term, a whole bunch of new physical properties are possible, including the coupling through resonance reactions because of the spin term to the background energy fields that exist everywhere in the universe.
This is actually something that I have some exposure to just through my old physics. It's called the zero point energy. And what this is if you think about the quantum mechanical nature of reality and virtual particles coming into existence, which we've experimentally confirmed. If you have two plates of metal that are very close together, then what happens is only waveforms that are harmonic within that range of those two plates can exist. Therefore, at the outside, any range of wave functions can exist. So what you can measure, and this has been done in experiments, is a pressure that actually pushes those plates together from what's called 0 point energy. Yeah. So what it's talking about is exploiting this particular thing. Now, whether you can exploit it, that's where we get into are you defying the second law of thermodynamics and so on.
But assuming that you can set up experimental conditions to invoke this reaction, this coupling, this resonant coupling with the background field, then you can draw energy from that background field and use that energy to overcome the Coulomb barrier. That's one theory. That's my favorite theory. There are some others out there that incorporate tunneling through the Coulomb barrier, which get pretty exotic. There are others that figure out how to reduce the Coulomb barrier. So there's a lot of work going on theoretically, but my favorite is you get enough energy to overcome it from the background field.
Right, but no one's done it. So it's all still theoretical at this stage.
Well, people, if you believe that cold fusion experiments are scientifically viable, that they're correct, which I totally believe they are. I think that's incontrovertible at this point. Then nature is doing it with the help of the experimental setups of people like Fleischmann and Pons. So experimentally, it's been happening, right? The question is getting
how do you replicate it? Yeah.
How do you understand it too? Because like the double plate. So this could have been the 0 point energy experiment could have been done by accident in the 19th century.
Correct. That's absolutely
because people could have two plates together and found, my God, we're measuring pressure here. Where the hell's it coming from?
That's exactly what happened. In fact, all of these effects came out of experiments that were anomalous according to mainstream physics, and that's really the history of science. So shouldn't be too surprising. So that is one source. And there are estimates that if we did get to this particular energy source, it would be 600 times up to, say, 600 times cheaper than anything we have available now per unit of energy.
Right. And that would get us out of the tight spot of the world ending. Through climate change.
Not through species extinction necessarily.
Right. Well, then you have to invoke the Jevons paradox and figure that out. Figure out the store or the problems that cascade off of solving the energy problem and therefore increasing output. So. Yeah.
Which is a bit, it's a big, this is, so you're saying, that there needs to be something which hasn't been replicated yet that.
No, it has been. But I want to be very clear. Yeah. It's been replicated actually probably thousands of times now, including by several components of the U.S. government, the Russian government, Japanese universities, the Chinese, and on and on. It's being replicated daily.
One point that you should make here is the Nature article.
Yeah, and just last week, Nature magazine published an article that wasn't. It said, it's an article about a research effort that's been funded by Google for the last 4 years, bringing together new researchers that were not in the cold fusion space for the last 30 years, brand new researchers, and said, okay, go run experiments. Let's try to get results and replicate. And they have not been successful. Now, they haven't been successful because they took a clean sheet approach, it appears, and they didn't take anyone else's input that's been in the field. And there's certain methodologies. Given if I had enough patience and a little bit of money, not very much, I could replicate one of these experiments. It just takes time and a proper lab setup. Right? Yeah. You can do this. This is not a mystery.
What is needed in that sense is not what Steve is saying here is if we realize the crisis we face, then we should be throwing a large amount of money at alternative energy research, even if you simply say, look, that's got to be wrong. Say, it might be wrong, but where we're headed, we've got to find something that works. And we simply have to experiment on a grand scale to work this out.
So, Phil, have we gotten you away from the edge of your seat?
Yeah, no, I'm firmly back. My bottom is firmly back in the middle of the seat now. So, and look, it's all interesting stuff, and we have run out of time today. But
there's more. There's more.
Oh, there's more. That was only the moderately crazy one, was it?
That was only the moderately crazy, but we don't have time, so maybe we can do it again.
Yeah, well, it'd be good to catch up at some point. I think the message is, yes, we do need to invest in alternative technologies because the model as it stands, the economics just don't add up.
That's right.
Yeah.
Exactly right.
Well, great talking to you. Have a good time in Wales. I'm not quite sure how still haven't figured out the cold fusion Welsh connection, apart from the fact it is cold in Wales. And maybe that's all you need. But we'll catch you again next time you're in town. Good to talk.
Thanks so much. It was a pleasure.
There we are. Steve Bannister and Steve Keen. We're all wondering now, what is the crazy idea? The really crazy one. Look, next time, the EU. Is it anti-growth? Back to just Steve Keen on that one. Join us for that. That's the next edition of the Debunking Economics podcast. I'm Phil Dobbie. Thanks for listening. If you've enjoyed this podcast, then please share it with your friends, like it on YouTube, and subscribe to this channel.